Hi everyone. We are gonna continue along our journey with learning more about functions. So today's topic is something called a one-one function and inverse functions. So let's gradually get into it. Let's build up to it. Let's start by recalling the definition of a function. So function is a relation such that for every input there must be a unique output, right? So for example, we said things like things we use in our daily life are functions, or they work as functions. So how do you want them to behave? When you turn on a switch, you want the light to turn on. You don't want a switch in your house where when you turn on, something random happens, right? So as far as possible, you want that the relationship between the output and the input is well defined. Now, because we can also put these functions into a coordinate plane, which we call the xy plane, where x represents the input and y the output, we end up with something called the graph of the function. And then using this definition that for every input there is a unique output, we create this test which is called a vertical line test. What it says is, I pick an input and I draw a vertical line, and if I get more than one output, then it is not a function. Right, so right here, this vertical line meeting this graph at 2 points means that if my input is this number, then there are two possible outputs. So this is not a function. Whereas for something that looks like a function, no matter where I draw the vertical line, there's exactly one intersection point. So this is a function. Okay. Also remember that we ended up with this definition of function because it makes sense, and we ended up on it from relations, right? A relation doesn't have any rules. So we add one rule that every input must have a unique output. And that rule leads us to a function. Now for certain scenarios, we want even more specialized functions. For this specialization, we create more restrictions, and thus we create new kinds of function. This new kind of function, we're going to call them one-one function. So what we do is we already require that. So what we require right now is if these are my inputs and these are my outputs, I already require that my input only goes to one line. But I can still have this situation where two inputs go to one output. Now I want to remove that. I want to say that we require that there is a unique relationship between each input and each output. Meaning, now you're only allowed lines which go all the way across. Okay, so let's see what that means. This means that for each input and each output, there's exactly one of them, right? Now, this is a function, right? This is a function. And this is a function as well. Now, if I pick any output and I go across, there is exactly one input. Let's say this function here is y equals x. So if I pick an output 3, then my input is 3. If I pick an output 1, then my input is 1. If I pick an output -2, then my input is 2. So this means that for every output, there is a unique input. So that satisfies this condition, and we say that this is 1, 1. Whereas the second function, which is absolute value of x, if I take the input 2, I can get the output 2, I could have gotten that output from the input 2 or from the input -2. So for every output except 0, there are 2 possible inputs, which means this is not 1, 1. Okay, just the word 1, 1 implies that one input, one output, one output, one input. Okay, so it's a two-way relationship. So the easiest way to formulate this to check is for graphs, just like the vertical line test, you draw horizontal lines. Draw horizontal lines. If they meet at more than one point, it is not 1, 1. Okay, so for example, anything that sort of does that, that's no longer 1, 1, right? Because there's actually 3 different inputs giving you the same output. Okay, so this function, this would not be 1, 1. Now algebraically, there is a definition. So what we want, let's try to get the algebraic definition. We want that if the outputs are same, then the inputs must be same. So by definition, it means that if f of x1 equals f of x2 implies x1 equals x2, then f is 1, 1. Let's unpack this definition. What is this saying? This says that whenever the outputs are equal, then whatever input that caused the output are also the same, then f is 1, 1. Okay, let's look at an example. It might make more sense. Is fx equals x cubed a 1, 1 function? So let's try the by definition one. So we let f of x1 equal f of x2, which means that's x1 cube equals x2 cube, which means x1 cube minus x2 cube equals 0, or x1 minus x2 times x1 squared minus x1 x2 plus x2 equals 0, and this gives me x1 equals x2. Okay, this the second one doesn't give me a real solution. So what's happening here? So this means that whenever the output is the same, the input is the same. So this is 1, 1 function. And graphically, cubic function, what do they look like? They look like that. So no matter where you draw a horizontal line, there's always going to be exactly only one point of intersection. Now, is x squared a 1, 1 function? Let's go by definition. So let's let f of x1 equal f of x2. So I have x1 squared equals x2 squared. x1 squared minus x2 squared is 0. But that means x1 minus x2 or x1 plus x2 is 0. And that actually gives me two solutions. x1 equals x2 and x1 equals negative x2. So this is not. Or you can just say like 2 squared equals 4 equals -2 squared, right? So you can also show a counterexample. You can just be like, wait, here is an output which can be generated by two inputs that are not the same. So 2 and -2 are not the same, right? Or you can just plot the graph of y equals x squared, and you can say clearly any horizontal line has two intersections. And the reason it's not 1, 1 is because exactly that, exactly what this says, that negative numbers, negative version of the same numbers also have the same squares. So they will never give you a different output. Show that this is 1, 1. So let's do it a couple of ways. Graphically is easy because what is that? That is just a straight line. And if you think about it, any straight line, for any straight line, if you make horizontal lines, they're going to meet at exactly one point. But you can also do it rigorously by definition. So you let f of x1 equal f of x2. Now what is f of x1? That's 3 times x1 plus 4 equals 3 times x2 plus 4. Solve this. I can subtract 4 on both sides, and I end up with 3x1 equals 3x2. I can divide by 3, and I actually end up with x1 equals x2. So yes, it is 1, 1. Again, let me reiterate what's happening in this process. In this process, we are saying this statement here says, it says if outputs are same, then this says then the inputs are same too. Okay, so this says if I let the output be equal for two inputs, then it turns out by doing the algebra that the inputs also were the same, or they had to be the same. And that tells me that for every input there is a unique output. So in our hierarchy of the things we have studied, we update, we have relations, then we have functions, and now we have 1, 1 functions. Okay, remember how all functions are relations, but not all relations are functions. Similarly, all 1, 1 functions are functions, but not all functions are 1, 1. Now that brings us to the end of this video, but in the subsequent videos we are going to see why this definition of a function being 1, 1 is extremely important in studying a different class of functions called inverse function, which in itself is a very important an important type of function that is studied. That's it for this video. Thank you.